much, Ben, for the introduction. So as Ben already revealed, so it will be about blockchains, and I will mostly focus from like the high level of blockchain, how to use it for programming, what does it mean to implement programming languages on it. So we can consider blockchain as a virtual machine, a new taste of a virtual machine that serves for distributed computing in a secure way where you have untrusted nodes. And here we can, like the more powerful blockchains, allow to run programs in a very like advanced way. It can be programs written in high-level languages like Solidity, which is an Ethereum language, but also Rust, JavaScript, and various other languages are supported. So it's really general-purpose computing. But at the same time, it's also a storage system in the sense that blockchain is used to store the state of the programs or parts of the state of the programs in a secure distributed way. There are various application cases, smart contracts, which the title says, but it goes far beyond. It can be any application. It's obviously it makes most sense where there's decentralized cases on untrusted basis. So I focus here on a very specific topic, namely the changes of blockchain programs. So once people have a blockchain program, they deploy it. It can be a smart contract or something more complicated. But then after some time, it's nearly always the case, there's need to change the program, be it because there are bugs, a feature extension, and other reasons. And then, like as usual in software development, there are two aspects to consider. One is changing the program logic, but also to retain the data, to migrate the data to the new program version. How does that look like? Nowadays, this is like not so easy, at least in a blockchain world. Still, it also poses in traditional software engineering. It's also sometimes quite involved. So if we look, for example, at the most prominent compute blockchain, Ethereum, it's a very simple model. So whenever a program, a smart contract has been deployed, it's non-alterable. It stays there forever. And then still people in practice need to be able to evolve the program. That's why they need to think ahead and design a so-called software architecture that is designed for switching the implementation later on. So what people do is designing a redirection system where they have like multiple smart contract components, designing a full application, and then they prepare changing the implementation by, in fact, having something like a pointer to another smart contract that is the implementation. So the downside here is extra programming work. Also, the data often lives in this proxy, like this first smart contracts for security reasons, but that also means that changing the data is very, very intricate. One can only map the data to a new form, but it's very limited. Also, I believe there's like a security risk involved there because the actual implementation depends on the value, like this redirection value, and that may be easily changed without that people may notice so transparently in the community. So whenever you use such an application, one needs to be very sure what's actually the binding behind it. May happen that at some later point, controllers of the smart contracts may then change it to another implementation with some logic that was not anticipated. So that's why more advanced blockchains have a dedicated upgrade mechanism so that it's more transparent, that people can even vote and review what's the new code to be installed, and if a majority decides this is safe to evolve, then that upgrade happens. So there's an institutionalized mechanism in the blockchain. But however, that's interesting to see when it comes to how from the implementation perspective, from the memory perspective, how is that the persistence implemented in those systems? There's still this reminiscent of traditional computing. So typically these blockchain programming languages and also blockchain implementations, they have several kinds of memories. One is the main memory that's very similar to the RAM or like the classical programming language, where you have like a volatile memory that is just there for a certain time of the program, and at latest when the upgrade happens, this temporary memory is typically erased and is gone. So that's why people, when they design blockchain programs, then have to think about the further longevity of the data. So similar to database management systems. So then there's like a secondary storage typical to disk, and if the blockchain is quite, let's say, used at a low level, then people even have to work on that secondary storage that's explicit memory accesses, and then comes with all the problems, safety, that this is secondary memory is not managed. You may like, have misinterpreted data or data corruption. And it's also quite expensive because the data needs to be constantly copied and serialized back and forth between these two memories, because the only memory to work on the data is typically the main memory. So this is a burden. That's why people then design wrappers on top of that, like frameworks or library, which ease that use of that secondary memory, that persistent memory. And this is just an example, but this then also comes with downside, like it's boilerplates. It's in the end very similar to these objects database mappers with all the aspects, and it's also performance-wise disadvantage because there's always serialization overheads. And we will actually thinking of how, at least with blockchain, one has like a new kind of a virtual machine, and also maybe a little bit of different approach of software engineering, how one could ease that in a very, very fundamental way. The most ideal one would be that the blockchain, the memory is anyways persistent. And if we could exploit that and have like the program being like living conceptually forever, but however enabling changes to the program so that the state of the program is automatically persisted, and the programmers can just use the main programming language, the core language concepts, like can design any graph style, object-oriented structures without needing to think about that. And this is then automatically, so to speak, the native program state is also your database in that sense. And so there's no like extra databases or secondary memories or special APIs involved, and this, especially in the blockchain programming world, makes sense because any programming complexity may be a security risk in that sense. If there are bugs, usually there's financial, like monetary values stored, and so this is like people tend to have like small size, or let's say like reduced complexity as much as possible. So that's what's known in literature as orthogonal persistence, so that the program state is naturally persistent, and we try to implement that and top it off with some extra aspects that we want to allow simple or also custom data migration to allow any kinds of program changes. And it's very important that the runtime system ensures data consistency such that people cannot mess up, like corrupt their data or misinterpret data. And we also aim for like good performance in that sense that we have very fast upgrades, and also data access has become very, very efficient. So I'm working at a foundation, as Ben mentioned, the DFINITY Foundation, which is somehow the main contributor to this internet computer blockchain. That's a powerful compute blockchain that uses WebAssembly as the intermediate representation on that virtual machine that I mentioned, and it has like one of these dedicated upgrade mechanisms. And for that blockchain, there are various programming languages supported, but however, there's one bespoke programming language, Motoko, that is designed to optimally support the concepts of the internet computer. So it compiles the WebAssembly. As flavor of the language is a little bit a mixture of C#, TypeScript, or Camel, so imperative, object-oriented, and functional. And very importantly, it's a memory-safe language that is garbage collected, so trying to avoid as many bugs or many hassles for programmers as possible when it comes to memory management. So just to give a little bit of a peek how an example, a very simple example in Motoko looks like. The basic components of the program are actors that can be deployed on the blockchain, and actors are stateful in that sense. They can have like variables here. That's the top level variables of the program. Here it's a very simple example of a log system, a message log system. So we may here declare a messages variable that is nothing else than a list of text messages with some functions to populate it and to retrieve it. A little bit like maybe the only artifact of persistence is this stable keyword, which means that this variable and also its transitive state is retained like forever or even across upgrades. So now we have this simple program, and then we want to evolve it, and we may add some functionality, maybe add some state, and later on we'll see we can also manipulate the data representation. And now I extend the program, deploy that new version, and then people can actually vote on whether they want to accept that, or if not, then this change will not be applied. So what happens here, we have like an extended version, but however, there's like a specific semantics in how the state gets, like on an upgrade, gets retained. So whenever a stable variable has already been declared in the previous program version, the system checks whether it's compatible to the new version, some changes can be done, then this is just retained. And in this case, the initializer is not executed, so there's like that code in this new version. However, we have a second variable declaration where that it was not there in the previous version. That means that the initializer will be executed. The initializer can reference other state that is around. Here, for example, the message object are shared by references, and then we can add functionality or replace functionality. So a little bit specific here, the programming language has two keywords for top-level variables. One is stable, which is like the most commonly used, and we plan to make it the default kind of modifier in the future. But there's like some, for backwards compatibility, some aspects to be considered there. And everything that is transitively reachable, directly or indirectly referenced from stable variables is considered persistence, and this is the state that needs to survive the upgrades. However, in certain cases, one may have like transient state that is maybe statistics that can be safely reset on an upgrade, and this can be declared flexible, and flexible means these are all the non-persistent objects that are solely reachable by flexible variables. These are retained just during the same version of a program. And of course, because of manipulation of references and so, there may garbage arise, and that's where the task of the garbage collector comes into play to collect the garbage objects. So I mentioned that the stable keyword is still an explicit keyword. There's a little bit of challenge. We cannot support all types for like long-term persistence, and it is due to the nature of functional paradigm of language. So whenever we have lambdas or promises, futures, this is something that is inherently transient, and it's very hard to map it to a new program version. Like actually local named function reference, that's something that's doable. I'm quite currently working on that. But somehow we have to restrict the type system in a way that not everything can be retained across upgrade, and we want to make it static. So this compiler checks whenever like this stable variable, that everything that is reachable from that, the static like fixture of types that can be reached from that is like fulfilling this condition. So that's the reason why we have that. And then when people want to make changes, the compiler and the runtime system supports what I call implicit migration. So there's an automatic handling on the upgrade, so nothing needs to be done by the programmers. These are kind of simple evolutions that can be done and that are safe from a memory mapping perspective. This is things like promoting types to supertypes, for example, adding and dropping actor fields, and so on. And anything that is more complex is then task of the programmers to implement that, like by custom migration, because there can be any kind of evolution that may be needed for a program. Just wanted to showcase like an example of a little bit of a more complex migration. This is actually like a refactoring migration. I've now introduced like these two variables, but however, maybe I want to group them to something like a logs list that is like pairs of text messages and the time when they were allocated. And this can be done in the language by two steps, like actually two upgrades in the sense. Like what we need to do is first do like an intermediate version where we keep the old declarations, because that's what's like retained by the implicit migration. Then we have access to the old state, but then may introduce new variable declarations with our desired like new type. And then we can provide with the initializer or specific additional functions, we can then add the copying mechanism, or like the logic that migrates that to the new variable. And then if we are happy, we can then at a later stage, this can also be part of the next like semantic upgrade, we can then safely drop the old variables. So the language somehow is prepared to also do complex migrations. That's how we do that. And the runtime system always checks whether any of those upgrades is compatible, like in the sense that it only has implicit migrations when it comes to the systems level. So in order to implement that, we had to do some changes, like in a sense, like the full stack, like the blockchain, but also compiler, the runtime system. First thing that is like specific to our blockchain, we had to somehow enable that the main memory, it was already persisted in the blockchain, but however just artificially erased on upgrade, just because classical mainstream programming languages cannot cope with retaining the main memory. So we had to somehow switch that off for Motoko programming language. And then also for historic reasons, we used VMIL memory 64 when it came to secondary memory, but not for the main memory. So that's because people just had like more temporary data stored in the main memory, then there was no need in having like a large scale main memory. But however, if we want to have like full power for the sense of orthogonal persistence, and we want to focus on the main memory for the implementation, we also want to have like the same capacity for the main memory. That's why we turned on memory 64, which is a WebAssembly proposal in a very far stage. And then an important thing is, why do classical like language implementation are not like by the off-the-shelf suited for this use case? That's because the compiler arbitrarily rearranges the allocations when it comes to static objects or so in the programs with every, let's say, change of a program, and that's something that we cannot use. So we have to have a design where a new program version is able to pick up the existing memory state that was left behind by the previous version. So for this reason, we designed what we call a stable heap, or like a heap design that is persistent, and where the compiler cannot make any whatever specific adjustments to where things are allocated. So what we have is some metadata that is like the anchor point, the root point, where every new program version, even if we change our runtime system, needs to start and see what's around in the main memory. And for example, a garbage collection state where there are root pointers in the dynamic heap, and then everything needs to be placed in the dynamic heap. So we had to get rid of all what many compilers do, static allocations, but only use dynamic allocations. And whenever there's something that used to be static, we do that by having a root pointer in our metadata. So a nice feature actually from WebAssembly was that we are also able to load data segments. So it's, for example, for literals in the programs, or like some static data that we do not need to denote a specific location in the main memory, but just keep that open, and then we can lazy load that at runtime to a dynamic address. And then everything else is on the heap. If we have like compile time known objects, something like static objects, we solve that by having a pool of such objects in the heap where we can look it up. So one extra indirection is needed, but that's the extra price of that. Also, we have a incremental garbage collector, because these can be quite large programs, can support up to 400 gigabytes like of memory per component in that blockchain. So a classical stop the world garbage collector is not working, even if we have a few gigabytes or so. This is also because the blockchain imposes a certain transaction limit, like one cannot have like arbitrarily long functions being executed, but they need to stop at some point. And then we piggyback the garbage collector on those function calls. And here with the upgrades, we actually want to have the upgrades very responsive. We don't want to wait until the garbage collector has fulfilled its whole round of increments until it's reached like a stage where it has completed its work. But however, we also want to perform an upgrade while garbage collector is on work. That's why we also designed the garbage collector state to be also persistent, and this proves to be very easy because we place the garbage collector state also in that metadata that can resume from that. And as mentioned before, like we have two kinds of roots. One are these stable variable, like the stable variables, and the transient variables are also root pointers for the garbage collector, and some other stuff, continuations. So very importantly, we want to have a stringent check when people like install a new version, that the new version is somehow compatible to the state that is around in the memory, because object may be laid out differently. That's why we support certain implicit evolutions that can be safely resumed from memory without having to change the objects. In the end, that's our motivation of defining these implicit data evolutions. And we enforce the compatibility by storing the types, the fixture of all types in the program into a very efficient way in a kind of a type table, and we check the type table that is existent from the previous state that is stored in the persistent heap with the new desired type table of the new program version. And if there's anything that does not fulfill our implicit evolutions, we reject the upgrade and roll it back so that it's like as if the upgrade was never happened. So this is just to ensure that these upgrades from the memory memory perspective stays consistent at all times. We used it at a type level and not scanning the heap again for like scalability purposes. We want to support very large heaps, so that's why here it just depends on the number of types, which is constant to the heap size, and that's why we enable very fast upgrades. So there's nearly nothing to be checked except this type table. So I did some excerpts of measurements, like now for this new orthogonal persistence for Motoko, that's the blue line, with this very cheap constant time memory compatibility check that just comes with a few thousands of instructions, 10,000 of instructions, just comparing it to an old mechanism that we used that was actually serializing all these objects that are reachable from persistent variables to the secondary memory. And yeah, apparently as expected, the serialization is something that depends on the heap size. And if this is just an excerpt for one example program, and here we clearly see that this is really like performing constantly. Why does this matter? Because as mentioned before, there's a transaction limit on the instructions. So assuming people have now a very large heap, they would suddenly run at the limit of the instruction, and then it could, with the old mechanisms, could no longer upgrade because there's too much to be moved around doing an upgrade. I was also interested to see how does that affect on performance, like when there's no upgrade, just an ordinary performance of the program, because now we can just work with the main memory. There's like no overhead involved in using the secondary memory. And also, and that's the biggest gain, programmers can now design any arbitrarily shaped data structures. They're no longer confined to a specific library where typically there is only a specific set of data structures that's around. Maybe it's a little bit unfair comparison, but I now had the challenge to compare Motoko with another internet computer implementation. I compared it against Rust, which also many people use. And in Rust, there's a library for enabling data persistence that's called stable data structures. And however, the library just has a specific set of data structures, like there's a key value store, like a B tree, there's some stable vector, like a stable list, and so on. And this is just excerpt in that sense, but it shows the only artifact that's mentioned for Motoko is still that stable keyword. Maybe you can get rid of that in the future. And there's way more boilerplate involved. And it becomes more complicated if you really have to map the data to like squeeze it into specific data structures that are around. And then I was trying to implement it as optimal as possible in both languages, and then measured what's the time of the accesses of reading out or retrieving elements in both systems. Here the difference is on logarithmic scale, and it's measured what we can't. We have a synthetic like performance measure on the blockchains because we cannot use wall time or so. It's something that needs to be deterministic. And what's measured here is the number of WebAssembly instructions. Some instructions are more cost weight, so it's weighted costs per instructions. And here it's really a dramatic difference. It's a logarithmic scale, and this is due to mostly modeling reasons. So in Motoko, you can just model cases. For example, if you have a queue, you can model it as a doubly linked list, but however, doubly linked list is not available in these stable data structures, then one needs to somehow map that maybe to a key value store, and the index denotes the position in the queue, something like that. That's why there's like, what I meant, like it's a difficult comparison. You have different possibilities in modeling it. Also here, to navigate like from object to object, like of the domain model, it's very easy. You can just dereference, and in the other world, you have to access have to introduce an index in like these stable data structures, retrieve it, copy it to the main memory, and that's why the difference is so high. To conclude, so we had like this aim to make smart contract upgrades easier in the way that it's simpler to use, but also safer because the runtime system guards it, less code, and it's also cheaper in the sense it costs less because the instructions is what you pay, the performance is what you eventually have to pay for. And we've done that with orthogonal persistence by pursuing orthogonal persistence to allow people to model data of any shape, like have full liberty of how they want to design and use their data, supporting implicit and any more complex data migration by explicit custom logic in a well-guarded way with these compatibility checks that check that at least at memory level there's no data corruption or misinterpretation, with very fast upgrades, constant time upgrades, and also very nice performance improvements when it comes to just running the program as a whole. Thank you for your attention.
We have time for probably 2 questions.
Do the actors run concurrently? Do the actors run truly concurrently?
I did not understand the upgrades to.
The actors run concurrently.
Do the actors run concurrently?
Yeah. The actors run concurrently. Sorry. Yeah.
How do you deal with the race condition?
Say again.
How do you deal with the race condition from the persistent data? How do you deal with the race condition?
So there's no race condition. Like there are race conditions, but data races inside an actor are not possible. But of course, you can design, because there's also an asynchronous programming model, and as everybody knows, like in JavaScript, so like any await point is potential for unconsidered interleaving. So it's not like addressing like race conditions in that sense, but however, importantly to say here, the memory management, which I explained before, is actually per actor. So every actor can actually have their own whatever persistence mechanism. So we may have like a ensemble of Rust implemented actors working together with this Motoko actors, and that's how we can combine, let's say, managed with less or like differently managed Rust. For example, Canis is combining orthogonal persistence with classical persistence approaches.
Thank you.
Welcome.
Any other questions?
Hi.
Hi.
It's still not working.
The very first?
I assume it's by running initializers. Yes.
Yeah. Here the initializer is a little bit hidden, but this is like what's the list map here. So I take the messages, like walk through the messages, and then it's very primitive. I just assign time 0.
So then, in the multi-step conversion, you could have added another step, which was to convert logs back to messages, just copying it over, and then the whole thing ended up just being a redefinition of messages.
So you mean here that I reintroduced
another step that says messages equals logs, and then another step that deletes logs, right?
Yeah, that's
and
possible.
So if I had just, it seems to me like you could automate this whole process just by saying, hey, I'm changing messages to this new definition. Here's the conversion function. Generate all these steps.
I completely agree. Like that's actually also something that we have in mind, because these 2 upgrades is still like an extra burden or so, and this is actually very easily to be done, that we can somehow define, let's say, more flexible migration to any new state. We are thinking of something like having a mapper function where one can access the old state but doesn't have to materialize it as new variables or so, and that would then ease these steps. Then you can just
some kind of annotation you could throw in.
Yeah. We thought about like providing a migration function or so that just applies if there's a previous state, maybe even multiple, that you can support multiple, like migrations from multiple previous version depending on what was around on the blockchain before. That's a good hint. Yeah.
All right, let's thank Luke again.
Thank you very much.